the left and with 10 kilohertz PWM excitation on the right. So these harmonics can be significant and they can impact the resulting NVH and the AC losses within the machine. Next. So to include the effects of the circuit on the motor, circuit schematic first needs to be created in Simplorer, and an FEA-based reduced order model can be derived from Maxwell to capture the fidelity of the magnetics to use with the rest of the circuit. Once in the circuit, the motor is integrated with the inverter and controller all together in one schematic. As the system operates under the command of the controller, the inverter will modulate its output to achieve the desired voltage for the needed operating points, such as a given speed and torque. So we'll see more details about this system integration and that process in a subsequent webinar. But the key capability for NVH is that the harmonically rich transient waveforms can be captured very accurately with small time steps, since the circuit simulation operates much faster than FEA alone. So this waveform data is then transferred back to Maxwell for a single period of excitation to capture the force densities distributions with a high fidelity. Next. So some of the results of this system integration are shown on this slide. On the left, we see the torque ripple or the torque results at 250 RPM without PWM on the top, so just pure sinusoidal excitation, and with the 10 kilohertz PWM on the bottom for that same 250 RPM. So what we see is the additional harmonics add ripple to the torque, and this additional ripple can affect the motor performance in the ways that we mentioned previously. So on the right, we see the equivalent radiated acoustic power at a range of speeds from 250 RPM up to 15,000 RPM. So on the top, we see the sinusoidal only excitation, and again, the bottom is with the 10 kilohertz PWM excitation. Harmonics begin to show up around 10 kilohertz, even in the sinusoidal only case, around 15,000 RPM. And this is because around that speed is when 10 kilohertz ends up being a multiple of the fundamental electrical excitation of 1 kilohertz for this machine and this pole count. So what we see on the bottom again is that PWM results show even more rich harmonic content around 10 kilohertz for all speeds, not just 15,000 RPM. And these harmonics spread forwards and backwards across the spectrum. So these extra harmonics can then be captured and utilized in waterfall, acoustics, and sound analysis, which will be discussed later on in this presentation. For now, I'll pass over to Irene to discuss some more high-fidelity analysis.
Thank you, Brian and James. So next I will shortly talk about force calculation, including motor eccentricity. Next slide, please. Okay, so there are multiple mechanisms which cause air gap eccentricity, including, for example, manufacturing tolerances and defects, as well as bearing wear. Independent on the source of the air gap eccentricity, it is a significant source of NVH and reduces the lifetime of the machine. Simulation can help to reduce the impact of the air gap eccentricity, and ANSYS provides the right tools to do that, including multiphysics simulation and optimization. Now I will show you how to model different types of eccentricity in ANSYS Maxwell and how eccentricity impacts the radial tooth forces. Next slide, please. So there are two main types of eccentricity, static and dynamic. Static eccentricity means that the position of the minimum air gap is fixed in space. This type of eccentricity occurs often due to manufacturing tolerances. Dynamic eccentricity means that the position of the minimum air gap revolves with the rotor. This type of eccentricity occurs often due to the bearing square. Next slide, please. In this example motor model, the air gap in the ideal case is 1 millimeter. To model static eccentricity, both motion axis and the moving objects are moved by 0.33 millimeters, and the minimum air gap position is fixed this way. To model dynamic eccentricity, only rotating objects are moved by 0.33 millimeters, and the minimum air gap position revolves with the rotor. And in both cases, the minimum air gap is 0.66 millimeters and the maximum air gap 1.33 millimeters. Eccentricities are implemented by the Maxwell eccentricity ACT, which is shipped with ADT installation. Eccentricity has an impact on most of the machine performance parameters, including, for example, torque and back EMF, but most importantly, it impacts the radial forces. Next slide, please. Here you can see the instantaneous force distribution on stator teeth surfaces, and on the next slide, hopefully we see the same forces animated. Next slide, please. Yeah, excellent, thank you. And as we can see, the forces are unevenly distributed when eccentricity is applied, and this has a significant impact on NVH, as we will see later. Okay, next slide, please. What we see here are the radial tooth forces with respect to time at the nominal operating point of this machine. The radial forces are obtained by integrating the force distribution shown in the previous slide over each tooth separately and taking the radial component. So the result is one force component per tooth. On the left, we see the forces for an ideal air gap case. As expected, the forces are symmetrical and periodical. In the middle and on the right, we see the forces for the static and dynamic eccentricity cases, respectively. Now there's a significant deviation of the instantaneous forces. And next, James will show how this impacts the noise level of the machine. Thanks, James, please go ahead.
Thank you. So I'd now like to look at how we can apply these electromagnetic forces that we've just been having a look at to a more detailed structural model than the simple analytical one used in the early phase analysis. So we'll be using ANSYS Mechanical for this, and we can use forces from Maxwell or from MotorCAD. This analysis could be extended to whole electric drive unit level, including gears and bearings, for example, using ANSYS Motion. But the focus for this series is on the motor itself, so we'll be focusing on the motor noise as opposed to the whole EDU noise level today. So we're considering the motor structure made up of the stator, the housing, the end caps, as well as the constraints provided on the housing by the rotor and the shaft itself. For a reasonable solution time, the windings are reduced to an equivalent mass applied over the stator slots. Typically, the windings do not contribute significantly to the stiffness, but if required, the combined effect of impregnation, insulation, and the winding metal could be considered directly in the model. So we're carrying out this analysis in the frequency domain, first with a modal analysis, and then a modal superposition using the forces described earlier from Maxwell. From the response, we use the surface velocity to extract an equivalent radiated power. This could be linked to an acoustic model, but in this case, we're looking at the ERP results based on the surface velocity. So applying this to the eccentricity cases described before, we can see that the static eccentricity case is relatively similar to the baseline, but with some additional noise at low speed. But when we apply the dynamic eccentricity, the once per revolution modulation of the fields means that as well as the low frequency unbalanced magnetic pull, causing noise directly, We also have many more frequencies appearing in the sound, as the higher orders are also modulated by that once per revolution rotation, giving the other orders seen here. So the graphical and numerical results are very useful, but to get a deeper feeling for the motor noise, it's useful to be able to hear the noise itself. We can do this very easily in ANSYS Sound, which also opens up a very wide range of capabilities for psychoacoustic and other metrics, as well as combining, for example, if you have pre-existing transfer path measurements or masking noise measurements, for example, aerodynamic noise around a vehicle, to understand the motor sound in a broader context. So here we can hear the three different eccentricity cases. First, the baseline. Then with static eccentricity. And dynamic. And really with that dynamic eccentricity case, you can hear how the overall sort of higher harmonic content in the sound gives a very different feeling to the sound overall. So it's also useful to understand some of the strengths and limitations of the simple analytical and structural analysis that I described earlier. So comparing some of the detailed structural responses to the earlier MotorCAD responses, what we can see is that the results are relatively similar between the full structural analysis and the simplified one, except that we have a large sound peak predicted for electrical order 6 in the detailed model. So if we animate this from the detailed model, we can start to understand why this is. So we can see that it's a coupled resonance of the stator breathing mode with the end caps in this case. And of course, this isn't considered within the simple analytical model. But what we're able to do now, comparing the simple result and the detailed result, and also being able to animate and understand the resonances here, is that we can understand design changes that could be used to avoid this coupled mode. For example, in this case, it could be as simple as increasing ribbing in this area to increase the stiffness. So the detailed analysis is still required to look at the system integration and the local modes, but really the aim is that it should be this detailed analysis should be providing additional value rather than being the first time the motor noise is predicted. So this avoids project risk, but it also means that because we're always pushing at the limits with our optimization and with our motor design generally, being able to consider all the metrics in the same environment means that we can get much closer to the overall optimum system rather than considering each part separately and having separate and relatively slow sort of design and modification and analysis iterations